Hello friends, in today's discussion we shall be talking about simple harmonic motion. In the physical world there are many examples of things that vibrate or oscillate, that is, perform periodic motion. Everyday examples are a swinging pendulum, a plucked guitar string, and a car bouncing up and down on its springs. The most basic form of periodic motion is called simple harmonic motion. In this lecture, we develop quantitative descriptions of simple harmonic motion. We obtain equations for the ways in which the displacement, velocity, and acceleration of a simple harmonic oscillator vary with time and the ways in which the kinetic and potential energies of the oscillator vary. To do this, we discuss two particularly important examples of simple harmonic motion: a mass oscillating at the end of a spring and a swinging pendulum. The universal importance of simple harmonic motion is that to a good approximation, many real oscillating systems behave like simple harmonic oscillators when they undergo oscillations of small amplitude. Consequently, the elegant mathematical description of the simple harmonic oscillator that we will develop can be applied to a wide range of physical systems. Characteristics of simple harmonic oscillators. Observing the motion of a pendulum can tell us a great deal about the general characteristics of simple harmonic motion. We could make such a pendulum by suspending an apple or any kind of small ball from the end of a length of string. When we draw the ball away from its equilibrium position and release it, we see that the ball swings back towards the equilibrium position. It starts off from a rest but steadily picks up speed. We notice that it overshoots the equilibrium position and does not stop until it reaches the other extreme of its motion. It then swings back towards the equilibrium position and eventually arrives back at its initial position. This pattern then repeats with the ball swinging backwards and forwards periodically. Gravity is the restoring force that attracts the ball back to its equilibrium position. It is the inertia of the mass that causes it to overshoot. The ball has kinetic energy because of its motion. We notice that its velocity is zero when its displacement from the equilibrium position is a maximum, and so its kinetic energy is also zero at that point. The ball also has potential energy. When it moves away from the equilibrium position, the ball's vertical height increases and it gains potential energy. When the ball passes through the equilibrium position, its vertical displacement is zero, and so all of its energy must be kinetic. Thus, at the point of zero displacement, the velocity has its maximum value. As the ball swings back and forth, there is a continuous exchange between its potential and kinetic energies. These characteristics of the pendulum are common to all simple harmonic oscillators, that is, periodic motion, an equilibrium position, a restoring force that is directed towards this equilibrium position, inertia causing overshoot, and a continuous flow of energy between potential and kinetic. Of course, the oscillations of the ball steadily dies away due to the effects of dissipative forces such as air resistance, but we will delay the discussion of these effects for the time being and take it up in later lectures. Mass on a horizontal spring. Our first example of a simple harmonic oscillator is a mass on a horizontal spring, as shown in this figure. The mass is attached to one end of the spring, while the other end is held fixed. The equilibrium position corresponds to the unstretched length of the spring, and x is the displacement of the mass from the equilibrium position along the x-axis. We start with an idealized version of a real physical situation. It is idealized because the mass is assumed to move on a frictionless surface and the spring is assumed to be weightless. Furthermore, because the motion is in the horizontal direction, no effects due to gravity are involved. In physics, it is quite usual to start with a simplified version or model because real physical situations are normally complicated and hard to handle. The simplification makes the problem manageable so that an initial idealized solution can be obtained. The complications, for example, the effects of friction on the motion of the oscillator, are then added in turn, and at each stage a modified and improved solution is obtained. This process invariably provides a great deal of physical understanding about the real system and about the relative importance of the added complications. Experience tells us that if we pull the mass so as to extend the spring and then release it, the mass will move back and forth in a periodic way. If we plot the displacement x of the mass with respect to time t, we obtain a curve like as shown in this figure. The amplitude of the oscillation is A, corresponding to the maximum excursion of the mass, and we note that the initial condition that x is equal to A at time t is equal to 0. The time for one complete cycle of oscillation is the period t. The frequency V is the number of cycles of oscillation per unit time. The relationship between period and frequency is V is equal to 1 upon T. The units of frequency are Hertz. For small displacements, the force produced by the spring is described by Hooke's law, which says that the strength of the force is proportional to the extension or compression of the spring, that is, F is directly proportional to x, where x is the displacement of the mass. The constant of proportionality is the spring constant k, which is defined as the force per unit displacement. When the spring is extended, that is, x is positive, the force acts in the opposite direction to x to pull the mass back to the equilibrium position. Similarly, when the spring is compressed, that is, x is negative, the force again acts in the opposite direction to x to push the mass back to the equilibrium position. We can therefore write F is equal to minus k into x. Here, the minus sign indicates that the force always acts in the opposite direction to the displacement. All simple harmonic oscillators have forces that act in this way, that is, the magnitude of the force is directly proportional to the displacement, and the force is always directed towards the equilibrium position. The system here must also obey Newton's second law of motion, which states that the force is equal to mass times acceleration, that is, F is equal to m into a. We thus obtain the equation of motion of the mass as F is equal to minus kx. Recalling that velocity v and acceleration a are respectively the first and second derivatives of displacement with respect to time, that is, a is equal to dv upon dt, which is equal to d square x upon dt square, we can write equation A in the form of differential equation as m d square x upon dt square is equal to minus kx, or d square x upon dt square is equal to minus omega square into x. Here omega square is equal to k upon m, which is a constant. Equation C is the equation of simple harmonic motion, and all simple harmonic oscillators have an equation of this form. It is a linear second order differential equation. Linear because each term is proportional to x or one of its derivatives, and second order because the highest derivative occurring in it is second order. The reason for writing the constant as omega square will soon become apparent, but we note that omega square is equal to the restoring force per unit displacement per unit mass. Mass on a vertical spring. If we suspend a mass from a vertical spring as shown, we have gravity also acting on the mass. When the mass is initially attached to the spring, the length of the spring increases by an amount delta L. Taking displacements in the downward direction as positive, the resultant force on the mass is equal to the gravitational force minus the force exerted upwards by the spring. That is, the resultant force is given by mg minus k delta L. The resultant force is equal to 0 when the mass is at its equilibrium position. Hence, K delta L is equal to mg. When the mass is displaced downwards by an amount x, the resultant force is given by F is equal to m into d square x upon dt square, which is equal to mg minus k into delta L plus x, which is again equal to mg minus k delta L minus kx, that is m d square x upon dt square is equal to minus kx. Perhaps not surprisingly, this result is identical to the equation of motion B of the horizontal spring. We simply need to measure displacements from the equilibrium position of the mass. Displacement, velocity, and acceleration in simple harmonic motion. To describe the harmonic oscillator, we need expressions for the displacement, velocity, and acceleration as functions of time, that is, xt, vt, and at. These can be obtained by solving equation C using standard mathematical methods. However, we will use our physical intuition to deduce them from the observed behavior of a mass on a spring. Observing the periodic motion shown in this figure, we look for a function xt that also repeats periodically. Periodic functions that are familiar to us are sin theta and cos theta. These are reproduced in this figure here over two complete cycles. Both functions repeat every time the angle theta changes by 2 pi. We can notice that the two functions are identical except for a shift of pi by 2 along the theta axis. We also note the initial condition that the displacement x of the mass equals a at t is equal to 0. Comparison of the actual motion with the mathematical functions in figure suggests the choice of a cosine function for xt. We then write it as x is equal to a cos of 2 pi t upon t, which has the correct form in that 2 pi t upon t is an angle in radians that goes from 0 to 2 pi as t goes from 0 to t. and so repeats with the correct period. Moreover, x equals a at t is equal to 0, which matches the initial condition. We also require that x is equal to a cos of 2 pi t upon t is a solution to our differential equation C. We define omega to be equal to 2 pi upon t, where omega is the angular frequency of the oscillator to obtain x is equal to a cos of omega t. Then dx upon dt is equal to v, which is equal to minus omega a sine of omega t, and d square x upon dt square is equal to a, which is equal to minus omega square a cos of omega t, which is equal to omega square x. So, the function x is equal to a cos of omega t is a solution of equation C and correctly describes the physical situation. The reason for writing the constant as omega square in equation C is now apparent. The constant is equal to the square of the angular frequency of oscillation. We have also obtained expressions for the velocity v and acceleration a of the mass as functions of time. All three functions are plotted in this figure. Since they relate to different physical quantities, namely displacement, velocity and acceleration, they are plotted on separate sets of axes, although the time axes are aligned with respect to each other. Figure shows that the behavior of three functions agree with our observations. For example, when the displacement of the mass is greatest, which occurs at the turning point of the motion x is equal to plus minus a, the velocity is 0. However, the velocity is at a maximum when the mass passes through its equilibrium position, that is x is equal to 0. Looked at in a different way, we can see that the maximum in the velocity curve occurs before the maximum in the displacement curve by 1/4 of a period, which corresponds to an angle of pi by 2. We can understand at which points the maxima and minima of acceleration occur by recalling that acceleration is directly proportional to the force. The force is maximum at the turning points of the motion but is of opposite sign to the displacement. The acceleration does indeed follow this same pattern as is readily seen in the figure. The energy of a simple harmonic oscillator. Consideration of the energy of a system is a powerful tool in solving physical problems. For the example of a mass on a spring, the mass has kinetic energy K and potential energy U. The kinetic energy is due to the motion and is given by K is equal to half mv square. The potential energy U is the energy stored in the spring and is equal to the work done in extending or compressing it, that is, force times distance. The work done on the spring, extending it from x prime to x prime plus dx prime is kx prime into tx prime. Hence, the work done extending it from its unstretched length by an amount x, that is, its potential energy when extended by this amount is u is equal to integral of kx prime into dx prime from 0 to x, which is equal to half kx square. Similarly, when the spring is compressed by an amount x, the stored energy is again equal to half kx square. Conservation of energy for this harmonic oscillator follows from Newton's second law. In terms of the velocity v, this becomes m dv upon dt is equal to minus kx. Multiplying this equation by Tx is equal to V dt gives m V dt is equal to minus Kx Tx, and since dx square is equal to 2x dx and dv square is equal to 2v dv, we obtain d into half mv square is equal to minus t into half kx square. Integrating this equation gives half mv square plus half kx square is equal to constant. Here the right hand term is a constant of integration. The two terms on the left hand side of this equation are just the kinetic energy K and the potential energy U of the oscillator. It follows that the constant on the right hand side is the total energy E of the oscillator. That is, we have derived conservation of energy for this case to be E is equal to K plus U, which is equal to half mv square plus half kx square. Equation D enables us to calculate energy E of the harmonic oscillator for any solution of the oscillator. Conclusion: simple harmonic motion is a type of periodic motion where the restoring force is directly proportional to the displacement. It can serve as a mathematical model of a variety of motions, such as the oscillation of a spring. Simple harmonic motion is typified by the motion of a mass on a spring when it is subject to the linear elastic restoring force given by the Hooke's law. The motion is sinusoidal in time and demonstrates a single resonant frequency. The frequency of periodic or oscillatory motion is the number of oscillations per second. The period T is the time required for one complete oscillation or cycle. A particle in simple harmonic motion has, at any time, kinetic energy and potential energy. If no friction is present, the mechanical energy E is equal to K plus U remains constant even though K and U change. So friends, here we come to the end of our discussion in this lecture. In the next lecture, we shall be discussing the pendulum and circular motion. Thank you very much.